All right, so in this video, we are gonna be looking at how we can use Newton's law of universal gravitation to calculate or determine different things about an object that may be orbiting, maybe it's near the surface of a planet, maybe you want to find something out about some unknown planet way out somewhere that you observe, whether that be a real planet or a hypothetical planet. We're going to take a look at a few different scenarios. Okay, now the first one we're going to look at is the orbital speed. Okay, so how can we determine the orbital speed of a given object? So what we're going to be doing here is figuring out how are we able to calculate the speed that the moon goes around the Earth, or that the sun goes around the center of the galaxy, or we go around the sun, that kind of stuff. Okay? Now, it's helpful to approximate any orbit as a circular orbit. Sometimes it will tell you it's a circular orbit. For us going around the sun, yes, we're elliptical, but we're almost circular. We can approximate to a circle. All right, so we have a force of gravity between the sun and the Earth. Okay, I'm just going to be probably using that a lot just as a basis, but I'm going to keep the symbols generic. So there is a force of gravity between the sun and the Earth. That gravity also causes a centripetal force. Since there are no other forces acting on planet Earth from the sun or even around it, we can say that the gravitational force is equal to the centripetal force. So the gravitational force between Earth and the sun is equal to the centripetal force between the Earth and the sun. All right. So let's create our equations. G m1 m2 over r squared for gravity, and m v squared over r for centripetal force. Okay. Now, centripetal force, you're used to this r being radius. Well, that works here, right? Even though this is the distance between the centers, as we're traveling in our orbit, the distance between the centers is also the radius of our circular orbit. Great. Because we know that, we can multiply both sides by r, which cancels this and that. Okay? So we're now left with just, I have a whiteboard, I can do this. Here. Okay? Great. Now, this mass is the mass of the orbiting object. It's the mass of the object actually traveling in the circle. Let's call, it doesn't matter which one we make here, but let's just say our m2 is that mass also, right? So m1 would be, let's say, the sun. m2 would be the mass of the Earth, where this mass is also the mass of the Earth. I can cancel that out, right? If I divided both sides, we're trying to find speed. If I had both sides by the mass of the Earth, we cancel that out. Okay, so I'm going to erase that here. Okay, and kind of simplify. And we're left with the orbital speed squared equals this gravitational constant times the mass of the sun divided by r. Square rooting both sides, we get v equals the square root of g times the mass of the sun divided by the distance between their centers, the radius of that circle. Okay? Now, this can be used in any scenario, but it's key to know that this mass here, the mass in the equation, is the mass of the object being orbited. So if you were to use this to find the orbital speed of some random satellite that we put in space, this would be the mass of the Earth, and this would be the distance between Earth and that satellite. The moon, this would be the mass of the Earth. This would be the distance between Earth and the moon. Okay, so this is something we can use to calculate an orbital speed. Okay, now that orbital speed is that tangential speed that you find right here, right? It just happens to work. Okay, we're of course going to assume that it's traveling at a constant speed, and that helps with the fact that this force will pretty much stay the same because the radius is the same because we're approximating a circle, so on and so forth. But this is what we're going to use here. Okay, great. Now, along those same lines, we can use these values and equations to find our orbital period. All right, where orbital period is how long it takes to make one full trip all the way around. Right? Yeah, we know for Earth around the sun it's a year, but what if we weren't dealing with just those particular values? Okay, well, let's start with our V equals square root of G M over R. Okay, we're going to end up starting with this because we have another equation with V for an object traveling in a circle, and that's 2 pi r over the time, right? The circumference divided by the time it took to make that trip. Since we're talking about period, I'm going to turn that into a capital T. It really doesn't matter. It's just I'm being picky. All right, so this is going to be the same speed. I can set these two things equal to each other. All right, so I'm going to erase just so I have a little bit of space. I'm going to rewrite those two things equal to one another. So we have 2 times pi times r divided by your period equals the square root of g, mass of the object being orbited, divided by the radius. Great. Now, just in order to get rid of this pesky square root, I'm going to end up squaring both sides. So we see that becomes 4 pi squared times r squared divided by period squared equals g m over r. Okay, now I'm going to erase and rewrite. That way again I have a little bit more space. 4 pi squared r squared over period squared equals g, mass of the object being orbited, times r. Okay. I'm solving for t, so I'll multiply both sides by t and then divide by your gm over r. So I'll end up with t squared equals 4 pi squared r squared divided by gm over r. Okay. A little complicated, a little kind of messy looking, so let's simplify a little bit. Again, I'll erase just so I have a little bit more space. Okay. T squared equals 4 pi squared r squared over gm over r. Since I have a denominator in the denominator, I can bring that up. So I'll end up with t squared equals 4 pi squared. Now, I'm multiplying an r by an already r squared, so that becomes r cubed divided by g times m. Okay? And now I'm just going to square root. Your period equals the square root of 4 pi squared r cubed over gm, which I can then simplify, if I choose, to be 2 pi times the square root of r cubed over gm. All right, so this is just another way to kind of look at an object orbiting. Yeah, it gets a little wonky because now we have this r cubed that we've never really dealt with before, but it works. Okay? Alrighty, moving on to the final scenario, the final application that we'll see. Now, in this particular case, it's a little different because we're not talking about an orbit. What this might tell you is, hey, maybe there's some object out there in space and we want to know something about its surface, right? Maybe in this case, the acceleration due to gravity. Okay, we're going to want to know that in case we ever decided to go visit it, right? If it's got too much gravity, human beings won't be able to survive on it, right? If it's got too little, well, we're just going to fly away and maybe there's not enough gravity to keep an atmosphere, right? All sorts of things we have to keep in mind. Anywho, it all starts with your Fg. Okay, we know from Newton's law of universal gravitation that Fg is g m times m over r squared. Okay. Now, we also know that when we've dealt with Fg, we've called that weight. And in order to calculate the weight of an object, all we had to do was just say, all right, we have Fg equals the mass of that object times the acceleration due to gravity, that local acceleration due to gravity. Okay. Well, when an object is near the surface of that planet, so that r is just basically the radius of that planet, these two values will be the same. So let's set those equal to each other. So we'll have m times g, little g, equals big G times m over r squared. Okay. Remember, this mass will be the smaller mass, so if we were to do this with me, for example, it would be my mass times 9.81 equals universal gravitational constant, that's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the Earth's mass times my mass divided by the radius of Earth. Okay. So what that means is we have my mass here, we have my mass here, let's cancel, boop, boop, and we're left with the acceleration due to gravity near the surface of whatever object it is you're looking at, gm over r squared. Cool. Now, one final thing I want to talk about before we wrap up this video is how might they ask you this? Well, they could tell you like, oh, we found planet Z and it has a mass of, that's 3 times Earth's mass, and it's half the radius of Earth. All right, calculate the acceleration due to gravity of that planet. Okay, well, we can just take our G, and then they'll say in terms of, the mass of Earth and mass of, or radius of Earth, so MERE. So we say, all right, we have this. Okay, where this is the mass of the planet, that's the radius of the planet, that is our G that we're looking for. And we'll say, all right, well, we have G, we plug in our 3 times the Earth's mass divided by the radius of Earth divided by 2, all squared. And just doing a quick calculation, we'll get 12G times the mass of Earth divided by the radius of Earth squared. Right? Now, since we know GME over RE squared is that 9.81, we can just say that is 12 times the acceleration due to gravity on Earth. Right? So that's kind of a way we can calculate it just based without having to actually know the mass of Earth or the radius of Earth. Right? So this was just a quick calculation there, but it's something that you can do. It's a trick you can use. Okay? Now with that, we'll see you next time.